So in this video, I'm going to talk about congestion control, particularly the basic motivation for congestion control in transport protocols and protocols in general, and then walk through the first example of a protocol that really identified and tackled this problem, TCP, particular version of TCP called TCP Tahoe. And I'll talk about the first mechanism that TCP Tahoe uses to try and deal with congestion, something called slow start. So the basic motivation for congestion control is that flow control tells an endpoint, say, Boston's going to tell San Francisco the amount of data they can accept. And so flow control specifies the limitations of the endpoint. However, it can very well be that this node in Boston is able to receive data much, much faster than the network can support it. So for example, while this node in Boston might have a buffer that allows it to receive 100 packets per RTT, it could be that some bottleneck link on the path from San Francisco to Boston can really only support about 5 packets per RTT. And so the idea is that if San Francisco communicates with Boston, this node in San Francisco communicates with the node in Boston at a rate which flow control would allow, then it's going to send packets much faster than the network can support. Most of these packets are going to be dropped, and it's going to spend a lot of its time doing retransmissions to recover from these heavy errors. You don't want to saturate the network because everything will work less efficiently than if most packets arrive. You'll require less control overhead. The rule will generally work better. And so the basic idea of congestion control is that endpoints should control their data rate so that they do not overload the network. This will generally increase the performance of the network. So if we just take a step back, in terms of congestion control, what really led to it as this very important area of study and of engineering in the internet, it all comes from TCP. So basic history of TCP in 1974, established it through a handshake, SYN, SYN-ACK, ACK. In 1978, TCP and IP were split. It used to be that the internet just, or at that point, the ARPANET just supported TCP, but they realized, we need to split them because we need stuff like UDP. Then January 1, 1983, that was the switch day when suddenly the entire ARPANET switched over to TCP/IP, IPv4. 3 years after that, the internet began to suffer congestion collapse, where links were saturated. They were sending, operating at line speed, yet no useful work was being done. Instead, all the packets being transmitted were unnecessary retransmissions or acknowledgements. So you're seeing full utilization of links while simultaneously no application level throughput. So then Van Jacobson, in this seminal paper, fixed TCP, figured out what was going on, and he published the seminal TCP paper which described TCP Tahoe. So these names, Tahoe and Reno, come from the versions of hardware for Berkeley Unix that these TCP implementations occurred on. And so you read about Tahoe, Reno, and then after that you start getting names like New Reno, Vegas, Daytona, just to follow that theme. But Tahoe and Reno were denoted sort of by versions of the Berkeley Unix that were distributed in the hardware they were for. So then about a couple of years after this first TCP Tahoe, fast recovery and fast retransmit, something that's in a future TCP version I'll talk about in a later video, TCP Reno, which they're common today, but at the time there were new ideas, were added. And so if you look, basically all TCP implementations today have the mechanisms that are in TCP Tahoe and TCP Reno. And so we're going to go through them in this series of videos. So there are basically 3 questions that a transport protocol needs to answer if it's going to provide reliable transport. Right? The first is, when should it send new data? That is, when should it send data which it has never put out on the network before? Second is, when should it send a retransmission? When should it try to retransmit data it has sent before? And finally, when should it send acknowledgments for data that it successfully received? These are these basic things as to when is it going to generate packets, right? Whether they're data packets, retransmissions of data packets, or acknowledgement packets. Now, of course, often we talk about data and acknowledgement packets as being independent, but in TCP they're not. The acknowledgements are simply a field in the header, and you can, of course, piggyback data and acknowledgements. But often we just talk about data and acknowledgements separately, just pretending that the flow is unidirectional, although often it might not be. It might be bidirectional. The point being that it can be that you have no data to send, but you do need to send an acknowledgement. So what did TCP look like before TCP Tahoe? So essentially, what happens is you set up a connection through a handshake, and an endpoint now has the flow control window size denoted by the window field of a TCP header. And so what pre-Tahoe, what TCP would do is, this seemed like a simple thing. It would just send the full window of packets. So if the window said, aha, I'm 30 kilobytes, it would send 30 kilobytes worth of packets. So this is obeying the flow control. It would then start a retransmit timer for each packet. And then if it didn't receive an acknowledgement for that packet, by the time the retransmit timer fired, it would then retransmit that packet. And so the basic problem this encounters, what happens if the flow control window is much larger than what the network can support? It might be that your endpoint has space for 30 kilobytes, but the link is already saturated. You can't suddenly just dump another 30 kilobytes on it. I mean, these numbers might seem small now, but back then, these were, you had relatively slow links in comparison to today's speed. So think of this more of like your Windows suddenly were advertised 30 megabytes. You don't necessarily want to dump 30 megabytes onto your DSL or your cable modem link immediately. So if you implement that algorithm, you just send the window of packets, what happens? Well, so here's a picture. So here it's showing on the x-axis is time in seconds, and the y-axis is the packet sequence number, in terms of kilobytes, so the sequence number of the byte that TCP has sent. And so what you see is on connection establishment, it immediately sends a full buffer of packets, about 20 kilobytes worth. And then it's getting some acknowledgement, so it's sending some more data. But then suddenly its window is a certain size, the flow control window, and it hasn't received an acknowledgement for this segment here. And so at this point, TCP is blocked, right? That here's these dots are showing the packets that are transmitted. So at this point, it's blocked in that it has sent up to the last acknowledged byte plus the window size, and it can't send any more. And the reason is that this packet probably was lost. So then here's the timeout, and it retransmits that packet. Then, as you can see, it's able to send a whole bunch more packets. It gets a whole bunch of acknowledgements. Or it gets a cumulative acknowledgement allowing the window to move forward, et cetera, et cetera. But the basic point to see here is that there are these huge sawtooths that you see big bursts of packets followed by idle timeouts, big bursts of packets followed by idle timeouts. And that many of these packets are redundant. Like this particular packet here is sent 3 times. Now this one is also sent 3 times. So you're seeing lots of additional retransmissions. And overall, the protocol is not performing very well. It's sending all these packets, but if you look at the actual slope of this line, in the sense of the data outsending, the slope isn't very high. If TCP were operating at line speed, operating at the correct speed, it should be following this line here. But instead, it's following a line with a much lower slope. It's actually sending data much slower than it should be able to. So this is what was observed, that TCP is very slow because it's sending lots of retransmissions unnecessarily, and there are lots of timeouts. So based on this, Van Jacobson proposed 3 improvements. The first is the idea of a congestion window. The second is better timeout estimation, and the last is self-clocking. I'm going to walk through each of those. The congestion window, I'm going to talk about in this video. In future videos, I'll talk about timeout estimation and self-clocking. So the congestion window. So the basic insight is that the flow control window is only about the endpoint. And so what you want to do is have TCP estimate a congestion window, that is, how much can the network support in the sense of how quickly can I send data and have the network deliver it reliably. And then the sender window is going to be the minimum of these two. In the sense that there's no point sending data faster than the network can support, nor is there any point sending data faster than the end host can support. And then what you do is, based on this idea of a congestion window, you separate how you behave in terms of sending packets and the size of this congestion window into 2 states. The first is something called slow start. The second is congestion avoidance. You use slow start when you're doing connection startup or when there's a packet timeout. When something has gone very wrong and you want to just back off completely and then figure out what it is that the network can support. Congestion avoidance, in contrast, is when you're behaving pretty well. That is, you're operating close to the network capacity, and so you don't want to start sending things much faster nor much slower. You're operating close to what you think the congestion window of the network is. So the idea of slow start is that what the node does is, rather than start its window at the flow control window size, it starts its window at a size of a maximum segment size. So basically one packet's worth of data. Today, nodes might start with 2 or 4. There's some sort of rules about that, 2, 3, or 4, but the original version started at 1. And then every time a packet's acknowledged, every time you receive a new acknowledgement, you increase this window by the maximum segment size. And what this means in terms of practice is that in the first round trip time, you're going to send a single packet, it'll be acknowledged. Now your window size is 2, so you'll send 2 packets, they'll both be acknowledged. You increase by 2, now you'll send 4 packets, they'll be acknowledged. You'll then send 8 packets. So there's this exponential growth. And so that's what you're seeing here. See, here's 1 packet, 2 packets, or there's 1, 2, 4, 8, etc. This exponential growth scaling up. So in a logarithmic number of steps, you can hopefully discover what is the congestion window size of the network. So this might seem, exponential growth is not slow. And so the name it can be a little confusing. The reason it's called slow is that it's slow compared to the prior approach. It's actually the much faster mode of TCP today. But compared to sending an entire flow control window of packets, doing this exponential scale up through a logarithmic number of steps was comparatively slow. So it's an interesting sort of historic compared to modern idea. And so we can see in this figure, this is also from Van Jacobson's paper, that the packet sequence number, is increasing this way, and you see this exponential growth. And then using slow start, you end up, plus then the congestion avoidance state that I'll talk about in a moment, you end up hitting this nice steady state. And while it takes you a little bit of time to discover what the line speed is, eventually the behavior of the protocol is very close to this line speed. And it's operating close to capacity. It's not overwhelming it, and you're not seeing these sawtooths of terrible performance. So that's the slow start state. So in the slow start state, you are increasing the congestion window by a maximum segment size for each acknowledgement. This leads to an exponential increase in the window size. The second state that you can be in is called congestion avoidance. And in this model, when you're in the congestion avoidance state, you increase the congestion window by the maximum segment size squared divided by the congestion window for each acknowledgement. What this behavior results is, rather than increase by the window by maximum segment size for each acknowledgement, you end up increasing the maximum segment size for each round trip time. So it's an additive increase. Whereas this is growing the window size exponentially, this is growing the window size linearly. So we have these two states, slow start and congestion avoidance. How do we transition between them? Well, really there are these two goals. One, use slow start to quickly find what the network congestion capacity is. That is, how fast can we send things before the network enters congestion and starts buffering packets and dropping packets. And so then once we are close to that capacity, you want to use congestion avoidance to very carefully probe. So we're below the congestion points. Let's just start slowly increasing until we reach it. Then maybe we drop down a little bit, then start slowly increasing until we reach it. We basically can use that to stay close to that value and be close to the network capacity. And we have 3 signals to accomplish this. Right? The first is if we're seeing increasing acknowledgements, that means the data transfer is going well. Maybe we can speed things up a bit. The second is if we have duplicate acknowledgements. Remember, TCP is using cumulative acknowledgements. So if we're seeing many acknowledgements for the same piece of data, that means TCP is receiving segments, but one of them is missing. So this means something was lost or delayed. The final signal is if there's a timeout. If we've sent a whole bunch of packets or a window of packets and we've heard nothing and there's a timeout, that means something very wrong has happened. Or maybe way off of what the congestion is. Maybe the network has suddenly become congested because it itself can have dynamic traffic. So this is the TCP Tahoe finite state machine. I'm going to walk through it bit by bit. So when you open a TCP Tahoe connection, you start in the slow start state with a window of a maximum segment size. And And recall that your actual window will never grow larger than your flow control window, the minimum of the flow control window and congestion control window. So this is controlling the congestion control window size. Then every time we're in the slow start state and we receive an acknowledgement, we increase the congestion window, this is C wind, by the maximum segment size. So this is the exponential increase here. Then we have a parameter SS threshold, which is this stands for slow start threshold. If the congestion window grows larger than the slow start threshold, then we transition to the congestion avoidance state. This means that, hey, we suddenly have a big enough congestion window, then we should slow down our growth. And so we transition to congestion avoidance. Now in the congestion avoidance state, if we receive an acknowledgement, increase the congestion window by maximum segment size squared divided by the congestion window. This is the linear increase. And so we see that the window size will look like this over time effectively, where here is when we hit SS thresh. And this part corresponds to this state, and this part corresponds to this state. But now what happens if we're in the congestion avoidance state and this linear increase goes beyond the congestion capacity of the network? Well, what's going to happen is we're going to see a timeout or a triple duplicate ACK. A triple duplicate ACK, this implies a packet was lost. We're seeing these many acknowledgements. And so what TCP Tahoe does on seeing either a timeout or a triple duplicate ACK is it resets the congestion window to be 1, and it sets the SS threshold to be the old congestion window divided by 2. And so what this is going to do is after, say, this, we see this linear growth, and then at this point, say we say a triple duplicate ACK, what will happen is that TCP Tahoe is going to set, we use blue, is going to set SS thresh to be half of what the congestion window is at that time. It's then going to re-enter slow start, do an exponential increase until it reaches this SS thresh, at which point then SS threshold, at which point we'll then enter congestion avoidance and do a linear increase. And so the way to think of this is that upon this triple duplicate ACK or this timeout, the TCP Tahoe has discovered what it thinks is too much, too fast a transmission rate. Its window is too big. So then what it does is it says, okay, I'm going to exponentially grow my window until I reach half of that point, and then I'll start linearly increasing it. So that way you can hopefully quickly get back to, close to capacity in a logarithmic number of steps, but then you don't want to get too close, and so you start at half of what that old value was, and then start linearly increasing again. So this is the basic finite state machine for TCP Tahoe. So here I will walk through a simple example. So we start with a sender, and let's just say SS thresh is equal to 4 when it starts up. So it's going to send a single TCP segment, single maximum segment size segment. The receiver, let's just call this 1. I'll number them as packets for simplicity. The receiver sends an acknowledgement. So at this point, here our congestion window is equal to 1. Now, since we're in the slow start state, it'll become 2. Becomes 2. And so the sender can send 2 packets, 3 and 4. The receiver receives them. 2 and 3. The receiver receives them, sends acknowledgements. Now our congestion window is 4, which means that we will send 4 packets, which would be 4, 5, 6, 7. Now at this point, congestion window has reached the slow start threshold, which means that TCP Tahoe is going to exit this slow start state and enter the congestion avoidance state. And so when these acknowledgements come back, it's going to increase the window by 1. And so rather than send 8 packets, congestion window will be 5. And you'll send 5 packets. So let's just say, I'll just draw one arrow here of packets 8, 9, 10, 11, 12. Now let's say that packet 8 is lost. It's dropped in the network. We've actually reached our congestion point. Well, what will happen? Well, the receiver is going to acknowledge 8. It's going to acknowledge that 8 was received. And remember, this TCP, so the ACK would actually say 9, but I'll just write 8 for simplicity's sake. So it's going to say, aha, I've received 8. Then 10, 11, and 12 arrive. Now TCP is going to then send acknowledgement 8, 8, 8. Because it's cumulative acknowledgements, it hasn't received 9, can only say I've received 8, I've received 8, received 8. This is a triple duplicate acknowledgement. We have 3 duplicates. So what now TCP Tahoe is going to do is it's going to transition back to the slow start state. My congestion window is 5, so I'm going to set my slow start threshold to be equal to half of the congestion window, right? So let's just say we're going to set it to basically just 2.5. And enter the slow start state again. So I'll send a single packet, right? Now this packet is going to be sent on a timeout. So essentially I'm waiting for the acknowledgement 9. I haven't heard it, I'll time out, and I will resend 9. Then that's the number of packets I can have outstanding. Then if an acknowledgement for 9 comes back, I can set my congestion window to 2. But this acknowledgement won't just be for 9 because it's received 10, 11, and 12. So what that acknowledgement is actually going to say is acknowledge 12. So I now have my congestion window to 2. I know 12 has been received. I can send 13 and 14. And I'm back in the slow start state until I reach this SS threshold, at which point I'll transition back to congestion avoidance. So that's a basic walkthrough of TCP Tahoe and how it behaves. It's moving between slow start and congestion avoidance, and how it's using triple duplicate ACKs in order to infer that something has gone wrong and return back to the slow start state. It's using that to infer that there's congestion and slowdown.